I want to start by discussing the generalized coordinates and how you figure those out, and so on and so forth. So somebody sent me this, I think Ertuğrul sent me this problem. I believe it's one of the homework problems from one of the previous semesters. And this is a example where you would need to use generalized coordinates rather than just simple Cartesian coordinates. Now, in this case, it's not too complicated. And I'm not going to solve the problem in its entirety, obviously, but I'm going to take a look at situations like this and see how we figure things out. Okay. Now, this is a very good example of the advantage of the Lagrangian method. So if you the last part of the problem is asking to obtain the equation of motion of the block by using the Newtonian method. And so let's just go over the problem. So we have an inclined plane, but it's free to move around its connection point to the horizontal, and there is some agent that's actually rotating it, and there is a mass that's at the middle of this plane, and it's attached with springs to the two ends of the inclined plane, and at the center the springs are at equilibrium length, and the length of the plane is twice the equilibrium length of the springs. Okay, so some configuration like this. I'm not going to put the numbers in, but this is our mass, and we are looking at the motion of this mass that's attached by the spring, and it's on this incline, and it's always on the inclined plane. So
hocam, on the figure on the page, the upward axis is z-axis, right?
what difference does it make?
No, I'm just trying to understand the question. So it is rotating around the z-axis, right? And the z-axis is towards.
It's rotating around this point, so it's rotating, like this. So the way it's drawn, it's rotating in the plane of the paper or in the plane of whiteboard in this case. Now, what may be attached to this, the axis perpendicular to that plane, is doesn't change anything very much. Did I understand your question correctly?
Yeah. I think I got it.
So it's just going around this plane. Okay? And obviously, it says some extension and so on and so forth, but we're assuming it's like a point mass. That's also evident from the fact that length of the spring is 2L, and length of the inclined plane is 2L, and it's assumed to be in equilibrium. So it's like a point moving on this plane. Now you want to call that Z. It's fine by me. Okay? So you can do this X, Y, and Z. This is fine. But that doesn't answer your equations. This is a two-dimensional problem. And since you're not going to be dealing with anything like the bivectors and things like that, we don't need to consider the axis perpendicular to our plane of motion. Now, what would you choose for this problem? Okay, so first of all, how would you do this with Newtonian mechanics? Right? So that's this can be done with Lagrangian mechanics in a proper way. Just that there are two ways. So the question is referring to Lagrangian equations of first kind and the second kind. So what we have been calling Lagrangian equations so far are Lagrangian equations of second kind. The Lagrangian equations of first kind are the one that involves constraints, and we're going to look at them today. But that's not important. That's how would you do this with Newtonian? So you know everything that's here from freshman physics. Right? There's some uniform rotation, and there's some springs, and there's gravity. So how would you approach this problem? Now, there's going to be some force on this that's coming from gravity. There's going to be a normal force that's just keeping it on the plane. There's going to be two forces which you can add up very easily, parallel to the plane, coming from the springs. And so you can draw a free path diagram. But there's a complication that this is rotating. So how does that change things? How would that change things?
So can we, when we have the free body diagram, can we also add the centrifugal force
We don't like
accompanying with the omega?
So we like, I don't know if this was emphasized in your freshman classes or afterwards, but centrifugal force is a fictitious force. And we'd like to use centripetal force, which leads to circular motion, and so on and so forth. You can add centrifugal force. Okay, I'll give you that. So you can add centrifugal force. But is that it? If I add the centrifugal force on top of that, am I home free? Is it going to solve my problem? So I have, these forces, like, for example, can you figure out the normal force? That's a problem, right? You can perhaps figure it out, but first you have to decide, are you done with the forces? Like, so you have the spring forces, you have gravity, you have normal force, you have centrifugal force, which is, in this case, going to be changing direction, but that's fine. We can just look at this for a particular value of this angle, theta. Is there anything else? So centrifugal force depends on how fast you're rotating and how far you're from the center, your position and the angular velocity. Is there another force? Did you see the, or did you read the book Dune by Frank Herbert? It's a classic science fiction novel. It's one of the big classics. And recently they made a new movie. I think it's the third one. So do you know why we have tornadoes? So there are these big, whirling parts of air that sometimes, cause a lot of damage. Why do they happen?
Due to some hot wind and cold wind getting together.
How do they get together though? There are multiple components of tornado, but why do we have this, rotational motion? There's something
Due to the
responsible for that.
rotation of Earth.
It's because of
It
rotation
also
of Earth.
happens with the water, right?
So the rotation of Earth, it would cause some centripetal force, right, or centrifugal force, but it causes something else. There's another kind of force that's caused in rotation. It's the Coriolis force. That depends on velocity. Okay? And it's easy to miss these things. So you can also add that one. You can add centrifugal force and the Coriolis force, and then you solve it this way. So if I was answering this in a homework problem, and somebody asked me to do this with Newtonian, which would be my first choice. Obviously, I will try to do this by Lagrangian or Hamiltonian methods. But you also have to add the Coriolis force. You need to know how that works. This is probably covered sometime in classical mechanics, but it's one of those things that people tend to forget. Right? But the Coriolis force is also responsible for the storms in the science fiction novel Dune. It's also responsible for the weird behavior of the coins in Space Odyssey 2001, if you've seen that movie.
Hocam, how is Coriolis responsible for all these? I mean, isn't it a hypothetical force? Like purely mathematical?
What do you mean hypothetical force?
I remember reading about Coriolis, and it says it's purely a virtual force. It doesn't exist in the real world.
Well, yes.
So how can it be responsible for physical phenomena?
Well, so centrifugal force is also responsible, is a virtual force in the same sense. But have you seen someone carrying like tea glasses and then turning around in a tray where it's connected, something like that? So
isn't that like the normal force of the tea on the tray? Like we call it centrifugal, but it's not actually. It's actually normal force. But we can't say the same thing about Coriolis.
Yes, you can. Yes, you can. So if the Coriolis force and the centrifugal force, so if you move to the rotating frame, then they are there. You have these forces. In the inertial frame, you're not going to have those. Okay? So, but this one, so if you try to look at it from the point of view of this mass, it's not an inertial frame. It's doing simple circular motion. Simple circular motion always has an acceleration. It's not inertial. Okay? So if you want to look at it from the inertial point of view, then you're not going to have that. But if you're going to look at it from the masses point of view, which I believe what the question is asking, you're going to have those forces.
Okay, thank you, Hocam.
So this is another complication. Okay, as you're changing from one reference frame to another. So if these are both inertial, there's no problem, of course. But if one of them is non-inertial, then you have to, keep track of your forces carefully. And if you just, write down the inertial forces here, we're going to get the wrong answer. This is a good exercise. You can try this. This is Arturo sent it to me. I don't know if it's available to other people, but I can put this on OptiClass. I don't like the style of the question because it's kind of like saying, okay, do this with the Lagrange equation of first kind and second kind and D'Alembert's principle and Newtonian. I think you should kind of pick up the best method. But the person who prepared this homework problem is also going to prepare a PhD Code 5 probably. So it's a good idea to get familiar with this kind of question. I might, in fact, prepare some like this, or see if the book has questions like this. But just because something is a virtual force doesn't mean that it has no effect on everyday life. It is going to have some effects. But my point here is not to discuss Coriolis force and things like that. We are going to come to that. My point here is that the Lagrangian approach here is going to be very straightforward. Okay? It's going to be easy to write kinetic energy and potential energy here. There are two kinds of potential energy, one associated with gravity, so that's just the height, and the height is determined by where you are on the plane plus this angle very easily. Or if you want, your x and y coordinates. Okay? So this is where you can put the origin here, so you can make your measurements easy, but you can put origin and the direction of these axes wherever you choose. Doesn't really matter. So your y coordinate is going to determine your gravitational potential energy. Your x and y coordinate is going to determine your, along with this angle theta, is going to determine your spring potential energy. Okay? And then the kinetic energy is just, the kinetic energy is just motion. Now, the x and y coordinates are not really suitable to solve this problem. It doesn't look natural. And I will choose your distance from the bottom over here, let's say some x over here, and then this theta. We can also call this r to make it look like polar coordinates. Okay? So sometimes it leads to confusion. I don't know. If you're comfortable with this r, then use r. If not, then just use x. It doesn't really matter. Okay? So that is much more natural for this problem. Why? Now, because the way I think about this, so let's go back to a simple problem, the pendulum, and see how we pick the. So this is my vertical, this is my pendulum. Let's say it's a point mass, it's some length L, fixed from some ceiling. Okay. Now, I have some position, x naught, y naught, say over here, and then I swing this pendulum, and it comes over here to some x1, y1. Okay. And I claim that this x and y are not good choices for your generalized coordinate, but this theta is. So this theta 0 over here, and some theta 1 here. Now, why? Well, in this case, it's because of the physics of the problem. And so as you go from here to here, how do you go about this? Right? How does this situation change? Right? So you're just moving along, and of course it doesn't need to be just two points. That could be another one over here, x2, y2. That could be even some excessively longer. Do you know what I mean? I hope. And that could be an infinite number of points that I can pick, and they all are going to go from one to the other, and so on and so forth. Now, how do you visualize this in your head? Right? You don't think of in x and y coordinates. You're thinking of this angle changing, right? So you can think of in terms of these, but then when you switch to polar coordinates, you're going to see that one of the polar coordinates is actually constant. So what you're changing is actually one parameter. Even though it looks like you're moving in 2 dimensions, you're not actually moving in 2 dimensions, right? Your path is like this. your path is one-dimensional. It's a simple curve, which immediately suggests that for the proper coordinate system, which might not be like orthonormal and things like that, but for the proper coordinate system, you're going to have one less parameter. Okay? So if this was looking like 2 dimensions, but you're restricted to a plane, again, you could switch to a coordinate system. It might look very weird, but you could switch to a coordinate system where you would get rid of one of your coordinates, the actual 2-dimensional motion, you're moving on a surface. You could be moving, it looks like you're moving in 3-dimensional space, but you're restricted to a simple curve, then you can get rid of 2. Right? So this is the idea. Now, there isn't, so you could, of course, try transformations and things like that, but there isn't a formal way that you can apply to every problem. But the way I think about this, that you look at the problem and see how it goes from one state to the other, to the other, to the other, right? Not just 2 points, but think of, infinitely many, or at least 3, 4 points. So as you go around this, you are not, changing X and Y. You are really changing a single angle. So the same thing here. Okay? So this is doing 2 kinds of motion. This is doing a motion in theta, and it's doing a motion on top of the plane. Right? So I wouldn't think of this as changing my X and changing my Y, which are tangled. That there's a complicated relationship between them, but there's a simple relationship between these 2. Right? Well, in this case, they're orthogonal. They don't have to be orthogonal. So you can always take a motion and divide this into little parts. You already did this, right? So the classical example that we give in rotational motion is that you take a wrench, you throw it in the air, and it does just something very complicated. But the center of mass moves in a parabola, right? And the big idea that allows us to solve that problem is that you can divide this motion into 2 parts: the motion of center of mass plus the motion about the center of mass. Right? Now, and they don't have to be orthogonal to each other. So in this case, they are. But let's imagine a case like this. So I have a little cart over here, and from this cart there is a pendulum that's swinging. This one is free to move over here, and this one is free to swing around the pivot point on the cart. Here's something like this. Again, this is 2 motions. The cart is moving, and all with respect to the cart, the bob is swinging. Okay, so what I would use in this case, again, not X and Y, but I choose some reference point over here, and this distance X from that reference point plus this angle theta. Okay? So the generalized coordinates that's suitable for your problem comes from the composition of your motion into simpler motions. So in this case, and this one, there's no decomposition of it. For these 2, the composition is obvious. Sometimes it's not going to be. Then you have to write down constraints and see if they're holonomic and so on and so forth, and use the method that we are going to go over today. Okay? And sometimes they are not going to be holonomic, and it's going to be complicated. But then there is really no general recipe. You have to do it really case by case. But if you can, the basic idea is to decompose your motion into simpler motions. So here there are 2 motions. There is rotational motion, plus there is radial motion. And as I said, that in this case, the 2 motions are orthogonal to each other. They don't have to be. Okay? Like here, there are 2 kinds of motion, and you can think of the whole thing on top of each other, and they're not orthogonal. Right? The swinging also has some motion in the X direction. That doesn't concern you. It's the motion of the pivot point plus the motion about the pivot point. It's exactly the same idea with the wrench going in the air, right? Parabola plus motion about the parabola. Without that, you can't do it. It's just too complicated. You need to take rigid body motion and define this motion about center of mass and so on and so forth. And if you try to define the moment, even just for something like a cylinder, if you try to define the moment of inertia with respect to arbitrary points, you're going to get a big mess. I mean, you can try, and artificially it could be a homework problem, but it's a big mess. Okay. Now, I'm not going to solve this particularly because there are some things in the problem that we don't see yet, but I think it's a good problem, and you can try And if you come up with any specific questions about the problem, I'll be happy to try to answer them. Rather than saying, I couldn't solve this problem, if you say, no, I tried solving the problem this way, and I stopped at this point because of such and such difficulty, then we have something to talk about. No, I couldn't solve the problem. Okay, I'm sorry. That's my response. Right? I cannot say anything else. And not because I'm difficult, but I'm not trying to be rigid, as you say in Turkish, but I really think it doesn't help. You really have to try yourself, have a specific difficulty, and then we can talk about it. If you can't even start the problem, then you have to start with a simpler problem. Right? That is fine. You can say that I tried this problem, but I don't even know where to start. Can you offer a simpler problem? That's a valid question. Yeah? But just saying I can't solve the problem is not a question, it's a statement. Right. Now, related to this,
Can you please share the question with us?
sure. Can you send me the email? So I'll put one of the class.
Thank you.
Right? Now this I want to. So last time I said I will discuss this motion of two bodies interacting with each other to motion of center of mass plus the relative motion. And I prepared some notes, but then I realized it's actually in the book. Okay. But since I did already prepare something, I'm just going to go over this. So it's in the book for the central force motion. So this the classical example of this is, of course, the two-body problem. The two-body problem can be reduced to a one-body problem by this procedure, but it doesn't have to be, gravitational two-body problem. It doesn't have to be the gravitational two-body problem. It can be any two-body problem. I'll try to keep this a bit more general, but let's go over this very quickly. So I have two masses. So let's say this is my origin, and I have one mass at R1, and I have a second mass at R2. Okay? And I'm going to define the relative position of 2 with respect to 1. So this is R, what is this? This is R2 minus R1, which I will denote by R21, but I also call this small r. And there's going to be some forces on these. So let's say the force on the first mass is going to be some external force plus the force on the first mass due to the second one, and the force on the second mass is some external force plus the force on the second one due to the first one. And of course, this F12 and F21 are equal and opposite to each other. Okay. So F12 is minus F21. Their magnitudes are the same, their directions are the opposite. Okay. Now F1, I'm going to say M1 A1, which is of course M1 R1 double dot, and likewise F2 is M2 A2, which is M2 R2 double dot. This is stuff you presumably know already. Now I'm going to define the center of mass. So the center of mass is going to be M1 R1 plus M2 R2 over M1 plus M2. Yeah. Now here the motion can be described in terms of the motion of these two bodies, but it can also be defined in terms of the motion of center of mass plus the motion about the center of mass. Okay? And you can also define it as the motion of the center of mass plus the relative motion of the two bodies. These are related to each other, but slightly different. Okay? So the motion about the center of mass will be the motion of this one with respect to center of mass. And in a lot of physical cases, this will be an inertial frame. Okay? Whereas the relative motion, the motion of this two with respect to one, is not going to be. Okay? I mean, if the mass of the second one is much smaller than the mass of the first one, it's approximately an inertial frame. But in general, there's going to be an acceleration of this one. And since you're measuring your position with respect to an accelerating body, That's not going to be in the inertial frame. Yeah, so there's a little distinction between saying that center of mass motion plus the relative motion, or center of mass motion plus the motion about the center of mass. So what I'm going to do is the first one, because that's much more commonly used, and plus one can be derived from the other very, very easily. Okay, so let's look at the relative motion. So that's the motion of the second body with respect to the first one. So R double prime is going to be R2 dot minus R1 double dot, and this is, as I defined over there, at A2 minus A1. And I'm going to write this using these expressions, and so just moving this masses to denominator and rearranging algebraically. So this is going to be F2 external divided by M2 minus F1 external divided by M1 plus, so this is the first terms in those force terms, F21 divided by M2 minus F12 divided by M1. Okay. So at this point, you have to do some simplification. You have to make some assumptions to make further simplifications. And the assumptions we are going to make is essentially dropping this one. So we drop this. Now, how could you drop this? I thought with the justification for this, there are two major cases. One could be simply that the external force is small. Okay? So if the external force is small, then you're fine. Let's say that you're, I don't know, just sitting there, and there is nothing, there's no force acting on it, it's just two bodies acting with electrostatic force, okay? An electron and a proton. If they are far away from everything else, typically there's nothing acting on them. But that's never the case, is it? Right? So there's always gravity, there's always the gravitational field of Earth. Yet in your quantum mechanics classes, you never ever take into account the effect of gravity on electron and proton. And it is important. You can't say it's unimportant. You can't say that the gravity is much weaker than electrostatic force and so on and so forth, because it's what's keeping the atom on Earth. Obviously, it's important. Okay? Another example will be that when you're looking at the relative motion of Moon and Earth, you don't take into account the effect of Sun. Now, is the acceleration caused on Moon by Sun larger or smaller than the acceleration caused by Earth? What do you think? Is the force due to Sun larger or smaller than the force due to Earth?
I'm thinking smaller, hocam.
Much larger, actually. That's the counterintuitive thing here. And yet we neglect it. Why? Because the second case, where this is these external forces small, is that when these are approximately equal. So if the gravitational potential due to Sun at the location of Earth and Moon is approximately the same, it's going to lead to the same acceleration. That's how gravity works, right? Given potential, different masses accelerate the same way. So these are my accelerations. So it's possible that even though this external force is large, this term is going to cancel out because it leads to the same acceleration on two bodies. This is very common, especially in gravitational force. The same thing for the hydrogen atom on the surface of Earth. Yes, Earth exerts considerable acceleration on both two, but it's the same. So you can neglect this. And of course, there is the mixture of these two, where this force is neither too small nor it cancels exactly, but there's a near cancellation. Right? So it's not a perfect cancellation, and the force is not very small, but the difference is very, very small with respect to what you get from over here. But the idea is that you drop this one for one reason or the other. And two common reasons are either there is no external force, it's small, or somehow it cancels. The accelerations due to this force cancels. Now, if you do this, and if you recognize that these are in fact the same thing, then we get F21 1 over M1, so 1 over M2 plus 1 over M1. Okay? And this we generally write as F21 divided by mu, where mu is going to be m1 times m2 divided by m1 plus m2. This is reduced mass. Now, so far I did not use any anything about the nature of this force. So to move further, say things further, you need to say something about this, but not too restrictive. So I'm going to erase these. But hopefully you can keep it in mind.
Hocam?
Yeah.
Is this also a very strict assumption? Because from the first chapter of the book, we read about strong action-reaction and weak action-reaction forces. If the action and reaction forces are not along the path that connects the two particles, then still we will have cancellation. But does it affect anything about our calculations?
Yes. So if the action and reaction doesn't hold, if these two are not equal and opposed to each other, you can't do this. There's no simplification. But what do you do in that case? I mean, what does it mean that action reaction doesn't hold? So it comes from conservation of momentum, right? Eventually, it comes from that. So if the action and reaction doesn't hold, then momentum is not conserved, which is not possible. Momentum is conserved. This is something we know. So what's happening in that case? Do you know the answer?
Which is forces come into play, I would say.
No.
So like,
well, maybe, but the explanation I prefer is that so the force is typically carried by a field, and in this case, the field must be carrying some momentum. So as the charged particles are moving around under influence of each other, for example, for the magnetic interaction, the action reaction doesn't hold, and in that case, the missing momentum is actually in the electromagnetic field. Okay? So a moving charge has a changing field, and a changing field carries some momentum. So that's the general explanation I'd like giving, but I mean, I'm not going to say your explanation is wrong. That this is a, usually there's more than one way to look at these questions. Yeah, but you're right that if the action and reaction doesn't hold, this is not going to work. So in fact, the force I want to look at is something like this. So it's a function of r. Remember, this r is the relative position times r. So it is along the line connecting these two, and it's only a function of the distance between them. So this is something very, very common. It's how the spring force works. It's how the gravitational force works, and so on and so forth. It's not a very, very, very restrictive thing. Now, in this case, if you take this, then your A, or r double dot, is going to be f of r divided by mu times r, and this f of r, we can write a couple of cases here. So it's going to be minus g m1 m2 by r cubed for gravity, and it's going to be minus omega square for spring. Okay? Sometimes we write it as minus k. Now for gravity, which is what we're going to see in the next chapter. So for this case, something more interesting comes out, and this is r double dot. When I substitute this in over here, we get minus g m1 m2 by r cube divided by, let's write the definition of reduced mass. So this one I'm calling just m, total mass, times r here. So the equation we get is r double dot plus gm over r cubed, r is 0. So it looks like the relative motion is driven by some central mass of capital M, the total mass. Oops, wait, this is. I missed it. Yeah, it is M1 times M2. M1 and 2 over M, right? Yeah. 1 over M. Which is not. Well, I don't know if it's surprising or not. I was going to say which is not very surprising, but that's perhaps because I've seen it a million times. But this is the equation that you get for relative motion. And it looks like there's an attractive central mass, which is the total mass, and you're just doing one body gravitational problem using the total mass, going on as total mass. Okay. One unfortunate thing that so this is standard exercise in celestial mechanics books, but in celestial mechanics, this thing here is typically called mu. So I use mu here for reduced mass. That's the general convention in classical mechanics. In celestial mechanics, the central attractive mass times the Newton gravitational constant is typically called mu. So if you encounter this with the mu, well, just something to keep in mind. Okay. But this is how you break down the motion into relative motion. It's very straightforward, but if you've never seen this before, then it's a little bit confusing. You just write down the relative motion, you substitute things in, you drop this. Sometimes it's just going to be 0, sometimes there's a good reason to drop it otherwise. And then you get this equation for the relative motion. And for the spring, if you substitute this one over here, then you're going to get the equation that we used already in the previous last week. Are there any questions to this? So because I did it now, I'm not going to redo this in detail next time. I'll just use the results. But if you have questions, I'll be happy to answer them or try to answer them. All right. Anything regarding the generalized coordinates? So is this, for example, here, we divided the motion into 2 parts. The motion of central. So what does this motion of central of mass look like? Well, the motion of central of mass is going to be, so our double dot center of mass. You can go over this using what we did before, and that's going to be, of course, M1 A1 plus M2 A2 divided by capital M. And remember, these are just the forces, so this is F1 plus F2 divided by M. But this F1 and F2 have the interaction force, which by our assumption is going to just cancel. Okay? And we're just going to end up with F1 external plus F2 external divided by the total mass, which is what you already know, that the center of mass is going to accelerate at a rate of the external force divided by the total mass. Okay. So here, this is one way to go about. Instead of using the coordinates of these two, R1 and R2, you can use the relative motion and the motion of center of mass. Okay. And notice that these are not orthogonal. Okay. So as the center of mass going this way, you could be going about sometimes in that direction, sometimes opposite to it, sometimes perpendicular to it. It doesn't matter. I mean, I'm not here like assuming I have some orbital plane and then center of mass is moving perpendicular to the orbital plane. Nothing like that. Center of mass can be accelerating in any direction, can be moving in any direction, doesn't matter. And the motion can be in any orientation. The orbital plane can be anything. It has to be in a plane. Angular momentum is conserved, but it can be any plane. Right? And sometimes this is more useful, sometimes it's more useful. Okay? It depends. And sometimes this R minus RCM, so this one is more useful. And R2 minus RCM. But all of these come down to the same thing. You're thinking of your motion as superposition of two motions. Okay? So one thing that you're familiar is the motion of center of mass plus the motion above the center of mass. It turns out that motion of center of mass plus relative motion works the same way, because there's a one-to-one correspondence between these pairs and these pairs. So this is motion above the center of mass. Okay? And yeah, just it doesn't really matter what you use, but the idea is you decompose the motion into simpler motions for which you can write simpler equations. Like you can write the interaction energy more easily, you can write the kinetic energies more easily, and so on and so forth. For the gravitational two-body problem, the reason why we resolve it this way is because we get this equation and we know the solution to this equation. And it's just a simple equation. It's in fact the second non-trivial equation we can solve in physics, the Kepler problem. I was hoping for more questions on this, but nothing is coming. So let's move on then. I'm gonna. We still have 10 minutes till break. Perhaps we can make some way. Now, so far our task, as I tried to emphasize, is to distinguish between realizable and unrealizable paths. Now, last time we used D'Alembert's principle for this, and D'Alembert's principle was sort of a differential. The differential form, right? So you're looking at each point on your path, and for each point you're imposing a condition. Sort of, so like this work has to vanish and so on and so forth. Now, today we're going to look at Hamilton's principle. And this is going to be an integral form. It has the same property that it uses Lagrangian, so it uses aggregate quantities. But this looks like this takes a look at like a more global view. Okay? So what does this do? Is that this looks at the motion over the whole path. So remember, our task is to distinguish realizable and unrealizable paths, and we are going to look at the not just single properties of the path, but the whole path. But of course, it's going to boil down to looking at the individual points. Obviously, something that's otherwise perfectly acceptable could be rejected because of a single point in the path. Now we have to define this, and the way I'd like to define this is through the configuration path. Okay? So when I say path, what I mean is the configuration path. So this will be like your positions, your velocities, etc., plus possibly time. So you have a path that you start at T1, that you end up at T2, and there's some parameterization. Okay? So this is your orbit, and T is the parameterization of this orbit. So it not only gives you, where you are at a given point, or what kind of path you trace, but at the same time it gives you your velocity, your rate of change, how you move on this, if you come back, and so on and so forth. Okay? And so this is going to be, say, for X and Y, if you are moving in two-dimensional space. So this is not something as a function of time. But if you were like doing something one dimension, which we are going to do, it will just be moving back and forth on a line. Okay? So how do you handle this? Now for this to work, for Hamilton's principle to work, we are going to have some properties Yeah. Apply principle. So to apply this principle, you're going to, I didn't state the principle yet, but I'm going to in a moment. We'll restrict ourselves to mechanical systems. And here I'm not using the mechanical system D'Alembert's principle. Okay, just systems we are interested in. Mechanical systems, all forces except constraints are derivable from some potential. Derivable is so this will of course speak multiple. So this needs to be position of velocities, positions, and possibly time. Okay. Now, such systems are called monogenic. And if the if V is just function of position, then system is conservative. Now, this is a little bit different from the definition we use for the freshman level physics course, right? But it's equivalent to what we did there. Okay, there's nothing contradicting this. Okay. Now, the Hamilton's principle. So we first define action. This humble verb is very, very important. So this is an integral I to L B, L being the difference of the kinetic energy and the potential energy. And this is a line integral. And over the path, over the configuration path. It's not a path integral, but it's certainly related to that, but it's a line integral. And you must have seen line integrals before. Where did you see it before? Just to remind ourselves what line integrals are. Where did you see it before?
Complex analysis.
Complex analysis, that's right. Yes, yeah. That's I remember. This is something I don't remember fondly. I really dislike complex analysis, but yes, it is there. But like some physics problem, there's a very famous one of Maxwell's equations contain this. Ampere's law, right? As you go around some configuration, a part of space, the line integral of the magnetic field is the current passing through that enclosed surface and so on and so forth. Yeah. So yes, maybe in Maxwell's equations you've seen it in differential form, but the integral form involves a line integral. And it's the same thing. Right? So you go over and you add things up. We are going to make this a bit more clear as we look at the examples. So that's the idea. Now, so Hamilton's principles say that. So Hamilton's principle, in motion, over the path time t1 time t2. I don't know if you can read what I'm writing, but this is expressed one way or the other in the book as well, so you can look at that for a more precise definition. So the motion over the path from time t1 to time t2 is such that I has a stationary value, or I is stationary. Value for the actual path, let's say. Or for the realizable path. So as you deviate from your realizable path, from the actual path, then this is going to, I is going to change its values, but since it's stationary for the actual path, the meaning of stationary is that as you deviate from the stationary point, the changes are going to be second order in the deviations. Okay, so the first order in deviations, the change is 0. Right, so this is something like when you're passing through a minimum of a curve. That at the minimum of a curve, if you make a Taylor expansion, the first derivative vanishes. So the first term vanishes. All the changes are going to be the second derivative. Right. So let's write this down. A simple example. F of x is fx0 plus x minus x0 f prime x0 plus x minus x0 squared by 2 f double prime x0. So this x minus x0 is our deviation. If we are passing through a minimum, if there's x0 is a minimum, then the first derivative is going to vanish there. And this change, as I go from fx to fx0, is going to be second order deviations. Right? This is something you know from calculus. The meaning of stationary is the same. So this function, the stationary, means that as I deviate from this actual point, then the changes, the difference between these two. So there's a path and there's a slightly displaced path. The difference between those two is not going to be first order in these deviations, but it's going to be second order. So the first order, if I neglect the second order terms, because deviations are very small, for example, then the difference is 0. So it's two ways of saying it. Either the change is in second order, or to the first order, it's 0. You'll hear both of them, and they are just equal. Okay? This is not to say that this is an extremum, though in the physical cases, it's going to be an extremum. Okay? But we're going to look at one example today where it is not. All right. So I'm going to take a break. So this is just an introduction. This is just definition. But we're going to pick up in 10 minutes from here. Then, and if you have any questions, I'm not going to erase this. So if you have any questions, we can just continue.